Section 9.2, and this is the critical value approach to hypothesis testing. So over the next few sections, we're going to have these different approaches: the critical value approach, the p-value approach, these different things. So pay close attention, make sure you don't get them all confused, okay? So, because they're going about the same way, they're just doing different things. So critical value approach, what's it do? It uses cutoffs based on the significance level of the hypothesis test. The criterion for rejecting the null involves a comparison of the value of the test statistic to the cutoff points. Alright, so here's our first example. And if I were you, I would write this down just so we don't have to come back to it so much, because I'm going to work it out actually on the next page, probably. That's what I'm going to be doing on that. So Jack tells Gene that his average drive of a golf ball is 275 yards. Gene is skeptical and asks for substantiation. To that end, Jack hits 25 drives, and the results are shown in the box to the right. The sample mean of those 25 drives, 264.4 yards. Jack still maintains that on average he drives a golf ball 275, and that his relatively poor performance can be reasonably be attributed to chance. At the 5% significance level, do the data provide sufficient evidence to conclude that Jack's mean driving distance is less than 275 yards? We use the following steps to answer the question. And here what we're going to do: A, B, C, and D. But notice what it says in the very bottom down there. For our analysis, we assume that Jack's driving distances are normally distributed, and that the population standard deviation of all such driving distances is 20 yards. Alright, so there's a lot of stuff given to us in this particular problem, folks. A lot of good information that is going to define how you work the problem. Number one that I noticed right here is our N, 25 drives. Here is our X bar. This is our sample mean. Down here at 20 yards, this is our population standard deviation. They told us that it was normally distributed, which tells us that z-scores may be involved, that there's a standard normal curve there somewhere. Okay, they gave us the significance level, which is very important. Alright, so lots of things in this that you need to pick out, okay, that should be clues to you as to how you're going to work this problem. So letter A, and I'll work as much of it here as I can. Letter A, state the null and alternative hypothesis. Well, the null is Jack's point. The null hypothesis here is that his average drive is 275 yards. Okay, that's his claim. The alternative is Gene's claim, which that his average is not 275. So letter A is pretty straightforward. Letter B, we're just going to discuss the logic of this hypothesis test. Well, basically, the logic of the hypothesis test is as follows, okay? Now, the null, if the null is true, then Jack's sample mean of his drives should approximately be 275. Now, we should not expect the mean of his drives to be equal to the population mean, because there's error and things like that involved. So you've got it should be approximately close. So, however, if it's too far away, if his sample mean is too far away, then we may want to reject the null and accept the alternative hypothesis, and Gene will be right that his mean is not 275 yards. So that's kind of where we are in terms of logic. Okay. Letter C, obtain a precise criterion for deciding whether to reject the null in favor of the alternative. All right, well, the first thing I see here is that it's normally distributed. So first thing that pops into my mind is z-scores. So what I can do is I can standardize this to get a criterion. And the way I'm going to do this is I know that since this is normally distributed, I know that the sum of the sample means is equal to the mean, which is 275 yards. And I also know that the standard deviation of the sample means is the standard deviation of the population divided by the square root of n, which is 20 divided by the square root of 25, which is 4. Okay, so I know that. And I know that to be able to compare things, if you remember from chapter 6, that's where the z-score comes in. That's where the normal curve comes in, because it allows us for comparisons. And so our normal curve here was this. We used to use this formula to find our z-scores. But for this particular problem, since we're dealing with our x value here would be the sample means. Okay, our x value would be the sample means. And our u here would be the mean of the sample mean, because we don't necessarily have our population mean, so to speak. We just have a population of the sample means. And then our standard deviation is going to be a standard deviation in relation to the sample. Okay? So what I'm telling you is this. Our standardized formula for this problem is going to be x bar minus 275, because that is our mean that we're looking for, all over the standard deviation of the sample means, which is 4. Now, the first thought that people have with this is that, Mr. Francis, that's the t-score, the t distribution formula, not the z. Hold on. Okay, remember we just substituted x bar and the population of the sample mean and the standard deviation for the sample mean in for our variables here. Okay, we just substituted those in for the variables there. It's not the t distribution. We know, number one, because it's normally distributed. T distributions typically aren't. Number two, we know the population standard deviation. It was given to us in the problem. That's not the case for t distributions. So that's how we know it's a z distribution. So I'm going to write up here so that we have it, or we'll go to the next page, so that we can see the rest of our problem. So our determining formula will be this. We will use it to help check our criterion. This is what we call our test statistic. Okay? Our test statistic. Now, so we need to figure out what our critical value is. That's going to be our value that determines whether we're going, whether it's going to be the determining line between reject and accept, basically. So we know that alpha is 0.05. We get this from the significance level, remember, which is 5% for this problem. Okay? So what this is we're wanting to find the z-score, okay, that has an area of 0.05 to its left under the normal standard curve. Now, how did we know we're looking to the left? So we've got a standard normal curve here, and we're wanting to find some z-score that has the area of 0.05 to its left. How did we know that? If you look at the alternative is a less than. sign. What does that mean? That means it is left-tailed. Left-tailed. So if it's left-tailed, that means everything, the area is to the left, okay? Everything to the left here, okay, is what we're looking for. So this will be 0.05 to the left. Well, how do we do that? We'll go to Table 2 in the appendix and look at the numbers in the middle. Find the ones that are close to 0.05 to the left. Remember, Table 2, you're looking at, it means to the left, so you're looking at the scores to the left. You should see in Table 2, I'm going to flip back here with you. In Table 2, what you should see is you should see two numbers that are close to 0.05. 0.0495 and 0.0505. So those two scores are both the same distance away from 0.05. Now, 0.0495 has a z-score of negative 1.6, negative 1.65. 0.0505 has this z-score. Okay? Now, how do you remember how we used to find the 0.05 since they're the same distance away? If you remember, we took the z-scores and we would find the average of them. We would find the average, which is negative 1.645 would be our average there. So this z-score here is negative 1.645. This is our critical value. So this is basically an answer to the question. I told you if it was too much smaller, if our sample mean was too much smaller than 275, that we would have to reject the null and accept the alternative. Well, your question should have been how much smaller is too much smaller? Well, this is too much smaller. Anything less than this is going to be too small. So when you convert it to a z-score, if your z-score is less than negative 1.645, we are going to reject our null in favor of our alternative. So if it's less, we're going to reject the null. If it's more, we're going to not reject the null. Okay? So this is our answer to letter C. This is our test statistic. This is what we are going to, this is our criterion, as it said for letter C. All of this here is our criterion to be able to test our formula. Well, to test our problem, excuse me. Letter D. Letter D said, apply the criterion in C to the sample data and state the conclusion. All right, well, we know from the problem that the sample mean is 264.4. So what we need to do is take 264.4 and we need to plug it in and change it to a z-score because we're comparing to this z-score here. So we've got to be able to look at apples and apples instead of apples and oranges. So change it, and you should get negative 2.65 for that z-score. So my question to you is, are we accepting the null or are we rejecting the null? Well, negative 2.65 is less than our critical value, We know less than. We got that from the original part of the problem, from the alternative here. It's less than. It's less than our critical value. So because of that, we are going to reject the null. Reject the null. So how much is too much less than 275? Well, once you change it to a z-score, less than negative 1.645 is too much less than 275. Once we've changed it to a z-score, that is. Okay? So, how do we interpret this? Well, we say this. We say at the 5% significance level, the data provides sufficient evidence to conclude that Jack's mean driving distance is less than he claimed. So basically what we're saying is that at 5% significance level, the data supports us to reject the null and accept the alternative, which is Gene's hypothesis that his driving distance is not 275. Okay? Please rewind this problem right now and watch it again. This problem can be kind of confusing at first, so please rewind it. I would even practice working through it separately, okay? And then go back and watch it and see if you got it right. All right, so here is basically what I was trying to say. Here's a good picture. I drew a picture of the rejection region and the non-rejection region with our critical value, but this is what it looks like in a professional setting. Notice our 0.05 area to the left here. Here's our critical value that we found. And because it was less than, the rejection area was to the left. The non-rejection area was to the right. Okay? So this is a nice picture for you to look at and be able to see what I was trying to talk about there. Now, what is the rejection region and non-rejection region? I think that's pretty self-explanatory for you. The critical value, that's the value or values, there can be more than one, of the test statistic that separate the rejection and non-rejection regions. A critical value is considered part of the rejection region. So I say that to say this. Even though our alternative just had a less than sign, because we came up with that negative 1.645, if we had come up with negative 1.645 from our data, we still would have rejected it. You got to treat it like a less than or equal to, or like a greater than or equal to, when you're reading critical values for rejection and not rejection. Critical values are considered part of the rejection area. All right, so here's the basic terminology for two-tailed, left-tailed, and right-tailed. Notice with the two-tailed, we're rejecting both ends and we take the middle, is the do not reject. The left-tailed is when it is less than, and notice it's rejected to the left of the critical value. Right-tailed would be a greater than problem. That's when we reject to the right of the critical value. Okay, so obtaining critical values. Suppose that a hypothesis test is performed at the significant level alpha. Then the critical value must be chosen so that if the null is true, the probability is alpha that the test statistic will fall in the rejection region. Okay, that will fall in the rejection region. All right.